I'm going to discuss section 13.4. Okay, this is our handout from that. That's in Anton's textbooks. It's about the definition of differentiability for functions of more than one variable. We've already seen partial derivatives and limits for functions of more than one variable in this section, or in this chapter. Okay, here's the definition of partial derivative. For instance, you fix a value, fix a y value, for instance, and then take the derivative with respect to x, and then plug in your point. Or vice versa, you can fix an x value and take the derivative with respect to y, differentiate with respect to y. So we know a little bit about that. We've interpreted that as the slope of the graph in the x or y directions. But we have not yet said what it means for a function of two variables, say, to be differentiable. It turns out that's a pretty complicated definition, pretty technical. All right. Now, it turns out it's not sufficient for just the partial derivatives existing at a particular point. We saw this example when we talked about limits. Okay, this function does not have a limit at the origin at 0, 0, because if we approach along the x or the y axes, you get 0. As you approach along the line y equals x, the function values approach 1/2, and therefore we have two different paths towards the origin for which the function does not approach the same value, so its limit is not existent. Alright, however, if you use the definition of partial derivative, alright, just plug into these definitions, plug 0, 0 in. Notice we can explicitly plug the origin into this piecewise defined function. We're defining it to just be 0, say, at the origin. Okay, then we would get that the partial derivative with respect to x is exactly 0. Right? You'd be taking the limit of 0 over delta x. If delta x is not 0, then that's constantly 0, and therefore your limit is 0. And likewise, the partial with respect to y, it would be 0 at the origin. But this function is not continuous because the limit doesn't exist there, so it cannot be differentiable there, no matter what that means. Okay, so we're going to get to that definition of differentiability by going back, looking at the single variable case a little bit more closely. All right, we're going to rewrite our definition, our limit definition of derivative from Calc 1. All right, but just remember what this is saying. This right here gives you the slope of the secant line, and that turns into the slope of the tangent line as h approaches 0. Right? This is an average rate of change here, and that turns into an instantaneous rate of change. All right, another way to look at that is saying that would be to say that your function can be approximated very well at your fixed point, your point in question, at your graph, which is x sub 0, and then the function value at that point, by a certain linear function. It turns out that linear function corresponds to the tangent line at the point. All right, now I want to go through a little derivation of this formula here because it looks a little strange with all the subscripts and the x sub zeros in there. Okay, so let's take a look at that. So our question is this: given a graph in the xy plane, here's your graph of your function, above a fixed point x sub 0, you're at your point on your graph x sub 0, f of x sub 0. What is the formula? What is the equation of the tangent line at that point? Okay. Okay, if you remember, right, just from your algebra days, the slope of any line is y equals mx plus b. From Calc 1, we know the slope of the tangent line is the value of the derivative, so it's going to be f prime of x sub 0. So we just plug in. All right, so plug into your formula, plug your slope in. Now, to determine the y-intercept, you need to know a point on the line, because any point on the line is going to satisfy the equation, and vice versa. We know one point on the line. It's x sub 0, y sub 0. So what we're going to do is plug that in for x and y into our equation. So plug y sub 0 in for y, x sub 0 in for x, and that'll determine the y-intercept b for us. That's the other constant we need in the equation of a line. All right, now doing that, okay, and then noticing also that the y sub 0, that's really the value of the function at the point in question. So this is the same as f of x sub 0. So we can plug that into our left-hand side there, and then solve that equation for b. Just subtract the f prime of x sub 0 times x sub 0, that number, subtract that over to the other side, and we've got b isolated. All right, once we have that, we're going to take that expression for b and plug it back into the slope-intercept form for a line, and that's going to give us our equation of our tangent line at the point in question. Okay. All right, so plugging this in, now we get the equations y equals f prime of x sub 0 plus, or times x, excuse me, plus the b, which we just figured out to be f of x sub 0 minus f prime at the fixed point x sub 0, the fixed number, times x sub 0. Now we notice we have two terms here that involve the derivative. Let's factor that derivative out, and then we'll be left with x minus x sub 0. Putting the function value first, this gives us our equation of our tangent line. Okay. All right, now we want to know what's the value at the nearby point, or how well can we approximate the value of the function at the nearby point with the value of the tangent line, all right, at the nearby point. All right, so the nearby point is going to be just a little bit, say, to the right of x sub 0. All right, so x sub 0 plus h. Now we're going to plug that x value into our equation for our tangent line. Okay, and that's going to give us the formula we saw on the handout. When we plug in the x sub 0 plus h for x, the x sub 0's cancel, and we're just left with h here. Okay, so that's our equation, or that's our approximation of the value of the function at the nearby point using the tangent line. That's the tangent line approximation. Okay, so now going back over to the worksheet, that's where this formula comes from. At the nearby point, that's our approximate value. All right, now where does this come from? That comes from the definition of derivative, so I'm going to go and explain that now. Okay. All right, so just writing that definition out, okay, this is our ordinary definition. This is limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 over h. What we're going to do is bring this number on the left-hand side, which is just a number. It represents the slope of the tangent line. We're using our properties of limits. The limit of a constant function is just that constant. So if that's a constant, we can say that's equivalent to the limit as h approaches 0. There is no h's showing up on the left of that number f prime of x sub 0. Same thing on the right-hand side. Now let's subtract the limit over. Subtract the limit of h as h approaches 0 of f prime of x sub 0 over. On the left and the right, we'll end up canceling this out on the left-hand side to give us 0. Okay. And then we'll have the difference of two limits on the left-hand side, on the right-hand side. Okay, so we're going to have the limit as h approaches 0 of this quantity, okay, minus the limit as h approaches 0 of just the derivative at x sub 0. Okay, now we just flip-flop sides here, putting that on the left and then 0 on the right. Okay, that has to equal 0. All right, now we're going to use a property from limits from Calc 1. We've got the limit of a difference is the difference of the limits, and backing that up, if we have a difference of two limits, we can say that that's the same as the limit of the difference of these expressions here. So we've got the limit as h approaches 0 of the slope of our secant line, or average rate of change, minus this number, which is f prime of x sub 0. All right, and that limit as h approaches 0 has to be 0. All right, now just rewriting this by combining by adding fractions, multiply top and bottom here by h over h. Think about that as f prime over 1. Then we can rewrite the limit one more time, and we get f of x sub 0 plus h minus f of x sub 0 minus f prime of x sub 0 times h all over h. That limit has to equal 0 as h approaches 0. Okay. Now, rewriting this one more time, we're going to factor out the negative here from these two terms. I'm going to rewrite that as the limit as h approaches 0 of f of x sub 0 plus h minus the quantity f of x sub 0 plus f prime of x sub 0 times h. Okay, and that's all divided by h. All right, and that limit has to be 0. Now, why do we go through all of this painstaking work to rewrite that? Because we saw just a minute ago that this expression is the tangent line approximation at the nearby point. It's a tangent line approximation at x sub 0 plus h. Okay, so this is showing that the value of the function minus its tangent line approximation divided by the distance to the nearby point must approach 0 as h approaches 0. Okay. All right, and that's what we've seen in the handout. All right. Now it just doesn't say that. The numerator is approaching 0, the denominator is approaching 0. So in order for this whole entire ratio to approach 0, we must have that the top goes to 0 faster than the bottom. Now, I got an animation to show for that. So here's the picture, and here's the idea. You've got, this is your error in your tangent line approximation. So at the nearby point at x sub 0 plus h, say, there's a value of your function. There is the value of the tangent line at that point. Here's your error in your approximation. As we go closer and closer to x sub 0, the fixed point, that error is going to shrink. Not only is that error going to shrink, but that error is going to approach 0 faster than our distance between the points is shrinking. You can see that error goes and shrinks to 0 faster than the distance between x sub 0, and my picture is 1, and the nearby point goes to 0. Okay, so it's backing this up a little bit. As we get closer towards 1, this error is getting smaller, getting closer to 0 faster than this distance is closing in towards 0. Okay, if we looked at that ratio, the error in the tangent point approximation divided by the distance to the fixed point, that's just h, that should approach 0. That's the definition of differentiability. Okay, so if I write down the error approximation, if I just put this side by side, I've got the error in the tangent line approximation divided by the distance to x sub 0. That's going to approach 0 as h approaches 0. So as h is approaching 0, the error is shrinking down.